I think I already posted the file, right? So I want to start with that, which is here. Yeah, so I would usually put all these files for that week on here, so you should find these. So I'll go through these slides, and then you should download this Rhino file, and that's what we are going to do. Open that as well, but it's fairly simple. So what do we do? So the assignment from last week was various additions of vectors, right, which was pretty simple. So basically we are gonna continue using that, but just like put it in the context of force, right? So I mean the actual structure. So we use those vector additions to actually sort of identify internal forces in each member, and yeah, so just give it a little bit of more reality. So this is basically kind of like step-by-step explanation of one of the questions that's in the Rhino file. I also do have text explanation, so if you want to read it, regardless of if you wanna or don't want to read it, you should read it. But this is kind of a simplified version. Yeah. So imagine I don't know what this is. I mean, it's a 2D structure, so it's not a tripod, but it's like a tripod. So imagine some sort of a two-legged structure, right? So I mean, there's no depth in this screen, so yeah, so you're living in a 2D world. So it's something like this. And I think we talked about the support types last week, pin joints and roller joints. We did, right? Yeah. But just to refresh, I mean, there are different support types, but the ones that you would see most often is pin joint and roller joint. The fundamental difference being, let me see if I have a slideshow here too. I think I did, didn't I? Structure 1. Yeah.
Can you make sure the sound is on when recording?
Yes, this time this is plugged in, so yes. Okay, so I guess I didn't show you guys. I show you the structure 2, guys, but it doesn't matter. So let me see, 327. Alright, so I'll make sure to include these, but no, not these. Okay, so here's a sort of different type of reactions at supports that you will see, and you're gonna hear these words like rollers, joints, or pin joints. What they are, pin joints pretty straightforward. If you imagine it's literally like a pin, right? So you can imagine something like this, which is, what it does is basically it can resist. For example, if I have these 2 bars connected at the pin, right? I cannot move this past each other because pins fixing the 2 bars, right? But it has absolutely zero resistance in terms of rotation. Like, it's completely free to rotate. So that's basically a definition of pin joint. But what's kind of brilliant is if you, depending on the number of those joints, for example, if you imagine a structure that I just showed you a second ago, which is like this. Imagine if 2 of those supports are both pin joints, and that at the top it's a pin joint too. So you have 3 pin joints. Each joint is completely free to rotate, but because of the geometry right now, it's more or less stable. I can like push on this guy, and it does not move either way, and it's resisting the force, right? So that's so basically the definition of the pin joint is, yeah, so you have resistance in axial direction, but it cannot resist rotation at all. Number of reaction I will get to later. We are not going to look at roller joint at this point. You will see it in near future. A roller joint is somewhat slightly counterintuitive. It's pretty intuitive up to one point. So basically, roller joint, pretty much literally, as you might imagine from the word, it's like a roller. And let's say this is resting on the roller joint. So roller joint has a resistance in vertical or y-axis direction. So like I cannot squish this thing, so it's fixed in this direction, right? It resists vertical loading, but it has zero resistance in horizontal loading, so it's free to move around. One last part that is slightly counterintuitive is it's also supposed to resist vertical uplift force too. So not only I cannot push this down, I'm supposed to be not able to lift it up either, so that's the only difference from what we have here and the actual roller joint. So that's kind of a side note, but don't worry too much about the roller joint at this particular moment. But anyway, do you understand that the three joints here are pin joint? So, and this is subjected to a load that's vertically going down at 50-pound force. So, so obviously, it's not hard to imagine, right? The point's not moving, right? You press down the points, but the structure is stable and static. So these legs must be resisting the force in some ways, right? So now we are going to look at we're going to focus on that point only for now. So again, since the structure is not moving, for all the forces acting on this point must be in equilibrium, which we talked about last week. Right now, the only force that we are seeing at this particular point is this vertical downward force. And if that's the only force that's working, then this whole thing must be moving downwards, right? So there's got to be a force resisting this 50-pound force. So in which direction those reaction forces would be working is pretty visible, right? Because these are sticks that's only capable, because there's a pin joint, we're not really, only forces that we are assuming to be in this bar is called axial force, which is parallel to the direction of the bars. So in other words, so there's a force either in this way, compression, or if it's being pulled apart, it's in tension. But we're not really thinking about bending this bar, right? So these bars are only experiencing the force that are parallel to its own direction. So in this case, if this 50-pound is pushing down, right, it's got to be pushing back up, right? I mean, as an intuition, right? If the whole thing is, if the reaction is pushing it down too, it's going to move down. So so it's not hard to imagine determine the sense of these reaction forces. So there's got to be a force pushing up this way, and since it's symmetrical, it's probably equal amount of forces on two sides. So it's literally like I'm standing on two legs, someone's pushing me down, and these legs are resisting the forces. So how are we gonna know? I mean, it's probably the way it is shown, these two forces that's acting against these downward forces, they seem kind of too big, and they are. And so how do we know the correct magnitude of each reaction, right? So here's what the vector additions that we did, and we talked about anti-resultant to keep the entire force system in equilibrium. here's where those come in, right? So now, if the structure is not moving, it means the forces in the system are in equilibrium, which means additions of all the three forces must be equal to 0. What's the last part? Also remember the graphical addition of all forces about the point will result in. Yes. So when the forces are in equilibrium, in other words, if the addition of all the vectors are, all the forces are 0, then when you complete this head to tail addition, the head of the arrows should come back to its start point, right? In other words, it's gonna form this closed polygon. So now we're gonna start drawing this force diagram. So the only known force right now is this 50-pound downward force. So we're gonna start by drawing literally at the same scale, showing this identified force here, right? And we can already kind of imagine the next two forces would be in this direction and that direction, right? So yeah, so we know that there must be a force that is parallel to one of the sticks. In this case, I'm showing the right leg first. So yeah, so there's gotta be a force that's parallel to this guy. So I'm gonna draw a dashed line here, knowing that there's gotta be a force either. It's gonna start here for sure. Do you see my cursor? Okay, cool. So it's gonna start here, and it's either gonna go this way or that way. From previous assumption, most likely it's gonna go this way, but what we don't know is where the next arrow is supposed to stop. Anyway, and then another thing that we know is if this is let's say this is the first one, next one is the second one. If this is the second force, we also know that there is this other force, and that's that's pretty much all the forces that are at this point. So there are three forces in total, and that third force must end at the beginning or start point of that vertical force, right? Because there are only three forces, and we know that the forces are in equilibrium. They add up to 0, so it must close on its own. So wherever this arrow goes, wherever the next arrow starts, it must end here. So the second arrow starts here, ends somewhere. Third arrow starts somewhere and ends here. So from those assumptions / conviction, we are now forced to conclude that this intersection of these two blue lines are where this second arrow must end and the third arrow must start. Yeah, the magnitude of these two forces can be determined by drawing the arrows from the intersection point of the two dashed lines. So second force would be here, third force would be there, and you would have this closed force polygon showing the additions of these three forces. So that must be the magnitude of these two forces that satisfies that condition, right? And that's at the correct scale. So now the force diagram is complete. So we're gonna transfer these forces. I mean, I didn't show which one's which, but it's obvious that this one went to the left side, this one went to the right side. So now we can show all the forces acting at this point, right? I didn't name the point, but it's the top head point. And here I just drew it in this PowerPoint thing, but if you drew it in if you either drew it very precisely on paper or if you drew it in Rhino or any other CAD software, you should be able to get the lengths off of these two arrows. Whichever force scale we are using, the length of that original downward vertical force, the length of that signified 50-pound force. So whatever measurement we get from these two arrows, we basically apply the same scale as the original, and proportionally speaking, we should be able to tell the magnitude of each of these forces, which ends up being, in this case, 27.95. So that's how we know the magnitude of these two forces. And that's about this point, right? So far so good. Any questions? No? Everyone's awake? All right, cool. So another thing is so we just looked at that one node, right? But basically, if the structure is static, not moving, and all the forces are in equilibrium, what we just drew is called free body diagram. Free body diagram, it's basically you take the structure system, you focus on one point, you kind of like cut it virtually, the structure there, and then identify all the forces that are acting at that point, and then to demonstrate that the forces are in equilibrium. So in this case, we drew a free body diagram about that point. But you can actually do that anywhere on these structures. Pick an arbitrary point and determine how the forces are in equilibrium. So now, let's say we want to draw a free body diagram at this point. So are the forces in equilibrium or not at this point? It must be, right? Because if it isn't, then that point must move, then the structure is moving. So anywhere you cut it, all the forces are basically in equilibrium. And so before I move on, so if you cut, let's say, at this structure, right? If you cut it here, how many forces are acting at that point, do you think? Anyone? How many forces are acting on this point? Let's imagine a rope that's hanging from the ceiling, right? I should have said sticks, but it doesn't matter. Let's imagine a rope that's hanging from the ceiling. You're gonna grab onto that rope, right? You lift off from the ground. You're hanging on this rope. So the rope is being pulled, right? If you not physically cut, right? But if you identify a arbitrary point on that rope and try to identify how many forces are acting on that point, name whatever one force that you can imagine. Right? If I'm hanging on the rope, what kind of forces are acting? Yes. Right, so I'm hanging on the rope, right? So my weight must be pulling the rope down, right? So that's one force. Is that the only force? If
force of the roof is the same.
Yes, so that rope must also be being pulled up by the same amount of forces, right? If not, then the whole thing's gonna fall down, right? So if you remember the very first class and that video that we looked at, even like if you're talking about a person standing on the ground, there's a gravity force pulling me down, but also the ground is pushing me up, right? So there's always a force and a reaction, right? Because if you're not moving, all the forces are in, the total of all the forces that are acting on you is zero. So if there's a downward force, there must be an equal amount of upward force, right? So that's actually, it's true here, right? At this point, my feet is pushing the ground down. Actually, let's say this, right? By my weight, and the ground is pushing me up. But then let's imagine right here, there's also a weight acting down and acting up. Otherwise, right, this point is going to move in space somehow. So that that balance that's achieved at one particular point in that structure, that's actually true along that line of action everywhere, right? So going back to here, right? So on here, there must be two forces that are equal magnitude acting towards this point. And they can only be parallel to this blue line, right? I mean, they cannot be possibly a force that's acting this direction or something like that, if that's the only thing that's working on this structure. So so actually if you pick a point in one of these sticks, you can see that there are two forces opposite to each other at the magnitude of same magnitude as this, because this is pushing down, right? The stick is pushing back. Therefore, the ground must be also pushing it up too. But if you pick a random point on this leg, then one force is pushing the leg in this direction, and the other force is pushing the leg in this other direction. Does that make sense? Similarly, that exact same balance is also achieved if you focus on the point at the very leg, right? So this stick is pushing this support down, and the support is pushing that leg back up. Yes?
So why is, if you cut it there,
Mm-hmm.
or at any point, why is the 50-pound gravitational force not included in those?
So basically 50, right? This downward 50-pound force got split into two directions now, right? So at this particular point, it's being pushed up, but if you move anywhere else, because so this is basically being split into two components, which is this and the mirrored version, right? Does it make sense? So here, let's see. So you're not gonna see this in the recording, but so right now we're kind of doing analysis of each point, right? So we did this. We are talking about the equilibrium about this point, so everything has to be zero, so that's how the forces are balancing each other, right? But in other words, I mean this, at that particular point, that's the applied force. But if you go to that point, or anywhere on the stick, so this is being resisted by these two forces. But in other words, also this. So that's the reaction force by these two. But also you can also see it in such a way that this force is now split into two components. So this force has two components, right? So basically when this pushes down, this splits into this component and that component along this stick, right? So that's why if you pick anywhere on this stick, this applied force, half of that is going to go to here, and the reaction at that particular point is equal to the reaction of that. Does that make sense? So we are showing the reaction here because we're doing a free body diagram with equilibrium, the sum of the force being zero, but you can we don't typically do these diagrams, but you can also argue that at this point this force splits into two. So if you want to translate that into these two directions, then it's going to be these two forces, right? So if you draw this diagram, this is not a free body diagram because it's not showing all the forces, but this is just graphically trying to show you this splits into these two forces, right? And that's why you have this and you have the reaction. So this would be the free body diagram at that particular point, and then that would be a free body diagram at that particular point or that particular point. So let's see, so that's at the support point. So now we're gonna go to that. So you can read more closely. This I showed more kind of rigorous step by step. It's really just the way. So this, you know. So again, if you look at this point, that's all the three forces that are acting, right? But if you take, for example, this point, you would have a force at any given point on this structure, you would still have a same reaction as you did here. And if there's that much reaction here, there's got to be the same exact amount of force in the opposite direction. And that's how you know this is the component of this guy on this side, right? Same thing here. Does that make sense? Okay, cool. So that's basically the first question, and so I think you should work on the second question. So one thing I kind of skipped on that demonstration because it's very simple is that it might be helpful for you to use these labeling methods. So maybe let me explain that as well, and then I'll leave you to try to solve the sample question too. So obviously I'm not gonna read each of these texts, but I mean, in this case, this process was so simple, so if you don't have to do this, you don't have to. But this can be applicable to more complex, like if you have more nodes, more members, this might start being helpful. But anyway, typically with this graphic methods, you start the force diagram first by placing this to the side. But also another thing that's helpful is we are going to label these zones that are between the forces. And just from the form of the structure that we know that there are some force in this member and that member. So we are going to label this zone here as A. This zone is B. And between these two forces, you go across, and this is zone C. So it's kind of it's kind of like if you look at that point Q, and if you sort of imagine the entire world as this round thing, then you can name that zone as A, and this is going to become B. This is going to become C. So you see how the world is divided by these three forces into three different pies, right? So that's why we're going to call this as zone A. This is zone B. This is zone C. So after we did that, on this force diagram, I'm showing this as BC. So there's some correspondence between the naming of the force between the left and right. So we're gonna call this force that's in between B and C. We're gonna use this sort of a clockwise naming system. So this will be called, it's gonna be between B and C, so it's gonna be called BC. So this would be called BC. And on the force diagram, if the name of this force is BC, we're gonna use the first part of the name, which is B, as start point, and second part of the name, which is C, as the end point. So this is gonna become BC. And and we're drawing the same diagram, right? So for some reason I started with this one, but this one is between A and B, so that's why I'm gonna call the next force AB. And from the naming convention we know that AB ends at point B. So I'm drawing this line that are parallel to this, assuming that there is going to be an arrow that's going to start at point A, which is somewhere on this line, and ends at point B, which is right there. So same thing can be done with the other leg, which is between C and A. So that's why I'm going to call the next arrow CA. We know where the point C is, we don't know where the point A is. So now we kind of left with this unknown point A that's on this line as well as on this line, which kind of gives you the only choice that the point A being at the intersection of these two lines to satisfy those two conditions. So that's how we kind of identify these points. And again, CA, force CA would be an arrow that connects point C and point A. So it starts from point C and ends at point A. Starts at point C and ends at point A. So it's like that. And then next one would be starting from point A and ending at point B. So it's starting from A, ending at B. So these two forces are in fact the two forces that we are going to identify. You get the lengths and you identify the magnitude of these forces. In this case I'm using 1 inch equal 1 pound force, so if you type the lengths, this is 50 inches, so that's why it's 50 pounds. The length of that is 27.95, and that's how we got the strength. So let's see. Yeah, I think we can do that. So now we have, for sample question 2, we have slightly irregular leg with diagonal applied force. So it's gonna be a little bit tricky. But now I kind of want you to try to, what should I do? Should I keep demonstrating, or maybe try to solve this, try to draw the same kind of diagram for question 2 for about 10 minutes, and then I would explain, right? If all I do is explaining, then it's not going to be a So the explanations are in the slideshow, and also you can read the explanation at the top, keeping the following the same direction. The only tricky thing is that so this case of pushing this point down, it was pretty obvious that two legs were gonna be in compression. But if you imagine pushing something like this from the side, right, it doesn't mean that you're always going to be in compression. For example, let's say, what if I push this point up from below, right? Then all of a sudden both of them are going to be in tension. So because what we are dealing with now is diagonal, it's somewhere between vertical downward and vertical upward, right? So you might have some tension member. That's the only kind of tricky thing, in which case the arrow direction is different. So in other words, so obviously this was pushing the point Q, all the forces are pushing point Q, so that's how we could tell that both of these sticks are in compression. But in this case, this is not right. But what if this was like this? If you find a force that's going away from the point, that means the force is pulling that point. So then that member must be in tension. So all I'm saying is you might run into that scenario in this question. So that's the only difference between this one and question 1. So I'll be back in 5 minutes and recap from there, I guess. Alright, so I saw some of you already starting the homework, so that's good. I posted it, right? Like I post the did I do that? Yeah. What? No. Did I do that? Two assignments. No, I didn't post it. But someone had the. How did you have that file? Anyway, okay. So let's look at this problem. I think some of you had it kind of right. So, but let's just go through this process. So again, we are going to be drawing a free-body diagram about that point. Yeah, maybe let's just follow the procedure, right, that's shown here, even though that's not completely necessary. So again, so we're focusing on this point, and I'm gonna start by labeling the world. So the zone between these two legs would be, I'm gonna call it A, and zone between this leg and this force, I'm gonna call it B. Zone between that force and this leg, I'm gonna call it C. And the reason why these legs can divide the world is, yeah, for sure there's going to be some kind of a force. We don't know what they are, but it's either going to be, for example, for the left leg, it's either going to be something like this or something like that. It can't be other than those two different directions, right? So there must be some kind of a force here, and there must be some kind of a force here, and the force divides the world into a smaller segment. So that's A, this is B, this is C. So now I'm starting by copying the applied force to the side to start the force diagram. Another thing we should know is that length of this arrow is 50 inches. That's signifying 50-pound force. So we are using a force scale of 1 inch equal 1 pound force. So let's just kind of write it down. So this force lies between zone B and zone C. We are using that, let's say, clockwise naming system. So we're gonna read everything in this direction, right? So because this force is between B and C, I'm gonna call this force BC. And when the name of the force is BC, that means on the force diagram, the start point of that force is B, end point of that force is C. So this is how it corresponds. This is BC, BC. This is BC, right? So let's look at this here. This guy right here. So there must be a force along this direction called CA, which means it's gonna start from point C. We don't know which way it's gonna go, but we know it's gonna be parallel to this one, and we know it's gonna start at point C. So what I'm gonna do is I'm gonna draw a line, and I'm gonna draw it as a dashed line, just to be kind of clear. So the force that is going to be here, whether it's like if it's gonna be like hold on, if it's gonna be like this, or if it's gonna be like that, or if it's gonna be like this, we don't know. But we know it's gonna be called CA. We know it's gonna start from point C, ends at point A. So point A must be on this line, which is parallel to this leg. So I'm just gonna put a point A with a question mark on this line. So it could be here, could be here, could be anywhere on this line. But one thing we know for sure is, for example, it won't be somewhere like here. So it's gonna be always on this line somewhere. So that's kind of all we can tell from CA. So we kind of have to leave it there. And then we're gonna look at force AB. Again, there's gonna be some kind of a force here that's parallel to this line. It's gonna start at point A, which we don't know the location of, but what we know is it's gonna end at point B because it's A, B, right? So now I'm gonna draw a line that is parallel to the left leg in dashed line in some sort of infinite length, and so that's the end point. That's where the arrow ends, and point A would be along this line somewhere because it's supposed to start from point A and be parallel to this line and ends at B. So now again, the only choice for point A now is intersection point between these two. That's the only point that can be on this line and on that line as well. So I'm gonna delete all of these A question mark. Oops. And now we have the definitive A on here. So now we can actually draw the forces. So again, let's look at the force that's going to be on the right leg. The force is going to be called CA, which means it starts from point C and ends at point A. So that's important, right? Because it's gonna determine which way it's gonna go. So it starts from point C and ends at point A. So therefore the arrowhead is on this side, which is close to the A. And the force on the left leg, it's going to be between A and B, and clockwise motion, it's going to be AB. That means the force that's to be here is going to start from point A and it's going to end at point B. So the arrowhead is on the B side. So now we can transfer these forces to the form diagram, right? The actual diagram that's representing the geometry of the structure. One thing to know is, okay, so let's start from the left leg, the force AB. The structure is like this, right? So we are trying to identify the internal force in the structure. So whatever the arrow is, it has to be on this structure, right? So it couldn't be like, even if it's even if it was a extension of that direction, we are determining the force that's in this structure. So for example, it cannot be like way out there, right? So force AB, which is this one, it has to lie on here and act on this point P. So the only way to, not point P, but that point. So the only way to put this force on this structure is like this, because we are analyzing those points. So the force AB is here, basically pushing against that point. So now we go to the right leg, right? Right leg, the force are going to be called CA along this line. Again, we're trying to determine the internal force on this structure. So this arrow has to lie on that structure and also touch that point, right? So as you can see, in this case, it's gonna go here, meaning, let me delete this guy, meaning that now it's a different direction, right? I mean, different, same direction but different sense. So now what this means is, let's just name that point as point P. So from this point P, applied force is pushing the point P, and this stick on the left side is pushing against point P, but this stick on the right side is pulling the point P away. And so that was the thing that I was saying first, right? And it's gotta be kind of slightly intuitive, because for example, this force, if you divide it to xy component, let me zoom in a little bit. This force that we are dealing with, for example, it can be divided into these two components, which is x and y, right, using that parallelogram law. And it does have this horizontal component which tries to push the point P to the left, your left too, yeah. So if you imagine something like this, let's say you are trying to push this way. I mean, you can even feel it if you, I mean, actually I'll pass it around, but it's kind of, it's not hard to imagine that if you try to do that, this is being pulled away from the ground, right? So that's why it experiences some tension. Yeah, so the rule of thumb is if you find a force that's moving away from the point, that means that member is in tension. So let me just kind of keep let's just do the free body diagram for this point and that point too. So we know that this member on the right leg must be in tension, so it's pulling the one end point. Let me start actually. So the rule of thumb for, we call it two force member. So these, whether it's a cable or sticks, right? Let's say you have this stick-like member and you have two endpoints, endpoint here, endpoint here. If the structure is not moving, right, and then if there's one force on one side, the force on the other end must be going to a different direction, because if the whole thing is doing this, that means this stick is gonna fly through the space, right? So we are only dealing with a structure that's not moving in space. So so these are called two force members because it kind of experiences the two forces. But there are only two configurations, right? So this, actually no, sorry. So I'm kind of identifying these are internal force that is reaction to the external force. So let me actually differentiate the internal force and external force. So what I'm showing here in blue is external, so that means it's And then let's see, let me visualize the stick. Alright, so it's a little hard to see, but so what you see in gray is the stick. In other words, that's the structural member, right? And the points are the endpoint of this structure. And what you're seeing in blue is the external force. That's some kind of a force that's acting onto this stick, right? And the yellow arrow is the force that is internal to that structure. So that's the internal structure, the internal force of the structure, which is what that member is doing, right? So this blue is pushing the sticks, therefore the stick is pushing back. And if you see that one, so if I'm kind of focusing on the yellow arrow, if that yellow arrow is pushing towards that point on one end, it must be also pushing towards a point on the other end. So basically the internal force configuration could only be this or that, right? Does that make sense? If it's this, then that stick is flying through the space, right? So it's these are kind of called two force member because you have this or this, right? So the graphical notation is if you see the endpoint, if the internal force is doing that member is in compression. So the one on the left is compression. And if you see this arrow, meaning the stick endpoint is trying to move towards the center point of that stick, that means it's in tension because it's trying to shrink, right? Does that make sense? Yeah? Right? Like if the ceiling is coming down, I'm doing this, right? So that's the left side, right? Yeah. Anyway, so kind of keep that in mind, right? So keeping that in mind, let's see. Again, that's compression. That's in tension. So keeping that in mind, so on the right side you have this. So it's gotta be that the force on the other end is this, right? That's the internal force. So then this member must be in tension. So if you look at, so if I were to differentiate the external force and internal force, that's the external force that's pushing the point P. This is the internal force in this stick that's trying to pull the point P away. So therefore, the internal force at the other end must be sort of the mirror of this guy, making this whole thing is in tension, right? And now if I am to draw a free body diagram here, the internal force is trying to pull this point away. If nothing is resisting that, this point is going to move away. So then there must be a force that's basically doing this, and that's actually an external force. Yes.
Wait, so it's not the other way around? Compression, like putting together and then tension pulling apart?
Right, so that's kind of important to differentiate the internal force and external force. So what you're seeing in purple here is internal force. So what's happening in this member, right? So let's say if and the blue is external force. So if I try to push this pen, right? what's gonna put this pen into compression is something like this blue arrow, right? You see this? If I push like this is gonna be in compression, right? This pen must be doing something because it's not being squished, right? It's not changing its length, or so it's not collapsing under my enormous muscle power. So the pen must be doing something, right? And what the pen is doing is this yellow arrow. It must be pushing back at my applied force here, right? So you can see the difference. So this is the internal force. It's pushing back at the external force. So that means that's why when you see this in the member, this signifies compression. Does that make sense?
So it's defined based on the external force. It's not the internal. Like the system, whether it's compression or tension, is defined by the external forces as opposed to the internal forces.
Right. Whether that member is in compression or tension, you can determine that by identifying what type of internal force is in that member.
Okay.
Yeah. So, yeah, I mean, it looks slightly confusing, but if you differentiate between external and internal, it must become kind of clear. So this is internal, that's external, right? This is internal. And let me show the because that's the stick, right? So same thing here. So the member's in tension if the external forces are pulling the member, meaning that these outward forces, the external force, but if this stick is resisting that external force, so it's actually, when you see these arrows, forces on two ends that's trying to pull back to its middle point, that's when you see this type of internal force, that means that member is in tension. So that's why, so these two internal forces signify that member is in tension. And if you were to draw a free body diagram here, the internal force is trying to pull this point away. So therefore there must be another force that's acting the opposite way, which is here, and that's the reaction at the support. That's what this support is doing. It's trying to pull this stick to prevent this from being sort of like yanked out of the ground, right? So let's say if this structure fails, for example, what happens if the structure fails from support being not strong enough? What happens is this leg is going to pull out of the ground, right? Instead of, as opposed to like sort of plunging into the ground deeper or something, because it's in tension. Just kind of trying to keep showing the same thing on the other end. You have this left leg which is pushing the point P at one end, so it must be pushing the other end, so that member is in compression, right? And if you were to draw a free body diagram about that support point, there must be a external force that's acting the opposite way, same magnitude, So in this case, the leg, so in this case, on the left side, the leg is pushing down into the ground and the support is pushing back, right? On the right side, the stick is trying to pull the support out of the ground, and then the support is trying to pull the stick back down to the ground. So that's kind of the free body diagram about these three separate points. That should be kind of it for, and that's 10:15. So I can upload the assignment, which has a very similar question. Let's see. Again, hold on, wait. This is a okay. So assignment. But there's probably gonna be another one that I'm gonna give you on Wednesday. So but anyway, week 3. So that's gonna be the first assignment of this week, which is gonna be a very similar question. I will also post on today's link basically I have the answer file from the exercise that we just did, so you should be able to see it. And that's kind of it for today. Any questions? Alright, so see you on Wednesday. I don't know, depending on, we would probably try to do a little bit more complex version of this 2D equilibrium, but then if that seems easy, then we're gonna move on to the 3D equilibrium, which is a little bit more complicated, so that's gonna probably take the entire class. See you on Wednesday.